All right, hi Margaret. I made some slides for my class about redox, and I thought I'd show you them here. It seems like some of the font type stuff is screwed up, so I'll try to fix it with the little Apple Pencil. This one's a really interesting reaction. Kind of historically, like when back in the country was making the railroads, they wanted to make the rails very stable and link them to each other. And so they created a molten form of iron that landed on the gap and made the rail stick together. And they used a reaction that looks at an iron compound, iron 3 oxide. I'm not sure you went through the naming, but that's what the name of that is, iron 3 oxide, because the iron are +3s, the oxides are -2. And if you put that in the presence of aluminum solid and basically give it a spark, it creates a tremendous amount of energy, which you could see in the photo, that's so hot it actually melts iron. Melted iron is the product with some solid aluminum oxide. So as I have in the slide here, this generates so much energy it's actually molten. It's kind of crazy. The liquid then cools and you have solid iron, and it keeps it together. This is not a reaction like the ones you were just doing with aqueous solutions, because look at the states. You have two solids that you basically put some fire by, and sometimes chemists use a little triangle to represent fire, and then the product is a liquid and a solid. So it's got nothing to do with water whatsoever. This is a redox reaction. A redox reaction is a reaction that exchanges numbers of electrons. When I was in high school, I learned Leo goes grr. Leo the lion goes grr. The loss of electrons is oxidation, and the gain of electrons is reduction. Now, just saying that sounds weird out loud because the students always say, what do you mean? Something gains something and you call it a reduction? That doesn't make sense. But you might remember that what you're gaining are electrons, and those are negative things. So if you're gaining negative objects, your total charge goes down, and that's why that's reduction. Some of the kids tell me in high school they learned oil rig instead, in which they just say oxidation is loss and reduction is gain. That's kind of a shorter version of that, but it's the same thing. So we're going to need a set of rules to apply to counting electrons. And I know it seems strange you're in college learning how to count. Chemistry class, you're counting in a certain way. So I don't have oxidation rules on this slide, but it's in my book. And so I'll just kind of take it from there. One of the things it says is that if you have an element all by itself and it says no charges on it, well, then the oxidation number is a 0. And that's basically what I'm writing here, oxidation number. Okay? If you have an element by itself and it has a charge, the oxidation number is whatever charge is attached to each ion in that statement. This is just one calcium, but it's an overall +2, so I'm going to write +2 there. And the same thing for the hydrogen, which is a +1. Now I know there's two of them, that's true, but each H itself is a +1. We'll get more practice about that as you go on. The other thing is, notice again that this program, PowerPoint going in to explain everything, doesn't do superscripts, so that's why the 2+ should be a superscript, but you can't see it there. Now remember the definition I just said about Leo goes grr? Look at what I do when I link together these elements. You can make a judgment of which one is oxidized or reduced if you remember the definition. So Leo goes grr. Loss of electrons is oxidation. So who loses electrons? Clearly, it's the calcium, because the calcium goes from a 0 to a +2. He must have lost 2 electrons. So that one got oxidized. The reduction is the hydrogen, because the gain of electrons is reduction. So this guy was a +1, he gained an electron and he became a 0. That's gaining, so that's a reduction. So H+ ion is therefore reduced. Notice what it says in red, obviously important. When one reactant loses electrons, another must gain them. The oxidation of one substance is always accompanied by the reduction of another as electrons are transferred between them. So what's interesting here is we had one calcium atom lost two, and they supplied two different hydrogen atoms with one each, and so everything has to balance. The next slide uses a different example, but also with some elements. So you could jump right in there and put zeros above the neutral elements. So copper metal and oxygen metal have oxidation numbers that are 0. This is a monoatomic ion, meaning it's copper with a charge, so it becomes a +2, and the silver becomes a +1. Remember again, just because you have two silvers, you don't account for that upstairs here. You account for the silver's +1 by writing it above. So I'll do +1 there. So who became oxidized and who became reduced? Well, the answers are kind of in the script here, but don't look at that. So if a 0 goes to a +2, what does that mean? Are you gaining electrons or losing? You're losing. So if I lose 2 electrons, that's loss of electrons is oxidation. This one is gaining. The +1 is gaining 1, and you're ending up in this state, which is 0. Okay? Notice that there's a 2 here, and so that 2 times the gain is going to equal the loss of 2. Got a new word for you here. When something gets oxidized, like the copper, it's also the reducing agent. It caused the reduction of something else. Silver ions is reduced. You want to guess what it is? It's the oxidizing agent. Okay? So that kind of tells the story of this reaction. It's a different one. All right. So one thing that students can get confused about is what happens when you have molecules that have multiple atoms in them. Well, the thing is that the rule says that when an atom is in a bonding relationship, this technique, this number counting system, gives the electrons to the more electronegative element that are being shared. Those charge assignments are called oxidation numbers. So it's a different counting method than you used before, but it's the counting method for redox. So here it is right here. There is a hierarchy. So what I mean is that if you have a rule, let's say number 5, seems to be in conflict with rule number 6, rule number 5 is more important. So let's look up at the top quickly. We already did a few of these. If an atom is a pure element like just pure copper, well then that's going to be a 0. If you have something that has a charge written on it, well then that's a +1. That's rule number 2. Fluorine is very powerful. It's almost always a -1. I'm not even sure I've ever seen an exception if it's combined with another element. If you have fluorine gas all by itself, well that's an element, so that's a 0. Alkali metals, I'm sure you'll mention that in your class. That's things like sodium and potassium. Sodium and potassium are always +1s. The second column, like calcium, is always +2. Hydrogen is a really important element in chemistry, and most of the time it's a +1 if it's connected to a nonmetal, like if you're doing water, H2O, you can just put a little +1 above the H. If it's connected to a metal, that's when it's a little weird. It's a -1. Okay, you know why? Because rule 4 is more important than rule 5. So sodium is always a +1, and therefore that forces the hydrogen to be a -1. Okay? Oxidation number of oxygen is a -2 unless the other element takes precedent. And I've already given you a couple of examples. Let me think. For example, look at this one. How about H2O2? That's hydrogen peroxide. Hydrogen has a higher rule, so that's a +1. That means oxygen is forced to be a -1. Okay? There's another compound called OF2. Rule number 3 said that fluorine was a -1. So in this case, this is weird, but oxygen's a +2. Okay? Halogens, that's like fluoride, chloride, bromide, iodide. The vast majority of the time you're going to see a -1. Now if it's bounded to an oxygen or a fluorine, then that could be weird. You know, you could have oh, I'm not sure here. Let's say BrO3 minus. That one's a challenge. Okay, the rule for oxygen is more important, so it's a -2. If I have 3 of them, that's a total of a -6, but be careful, the whole thing is -1. So how do I add a charge to bromine to get an overall -1? It has to be a +5. Okay, you see what I did there? I have 3 different O's that are each -2. However, I need to have an overall -1, and the proper number to do that is the +5. Notice that the overall charge must equal the sum of all the oxidation numbers. So that's kind of what's happening with this bromate one. Now remember, don't just add these 2 numbers in there. It's each atom individually. So really the +5, a -2, a -2, and a -2, if you add them all up, that's a -1. Okay? Why don't you practice some of these or listen to me do them? So H2S uses the hydrogen rule to attach a +1 there. That means that this sulfur must be a -2. I don't remember, I don't have the rule numbers in front of me, but there was a rule about halogens. Halogens are almost always a -1, therefore in this molecule, sulfur is a +2. This is an ionic salt, sodium sulfite. The alkali metal rule is the highest rule, that's a +1. The oxygen rule is -2. So let's see. If this whole thing is a 0, because I have no charge here, how am I going to get up to 0? With a +2 and a -6, this has to be a +4. Sulfur, as you can see, is a versatile little bugger. Oh, this is actually a mistake here. Sulfate is SO4 2-. If each oxygen is a -2, this sulfur must be a +6 in order to get the total charge that I want. All of this added up together is a -2. Okay? Finally, this one is a challenge because it's a bunch of different elements. Let's assign the numbers first and then we'll answer the question about a redox. All right, so I have an element here of copper. That's a 0. I have oxygen is -2, hydrogen's +1. That means I have, whoops, my bad, I'm going to go to an eraser here. Figure out how to use my program here. There we go. Go to the pen. And I've got a -2 and a +1, and this must be a +5 for the nitrogen, right? And then I've got, I know nitrate as a whole is -1, so this is going to be a +2. The oxygen's -2, and this is another +5. So nitrate, there you go. Oxygen is -2, nitrogen is +2, water is -2, hydrogen's +1. All right, so I've got copper. Here's my arrow here. I've got copper 0 going to +2, so that lost 2 electrons, so oxidation. And I have nitrogen. Oh, this is interesting. Look at this. I've got 8 nitrogens. They started out as +5. Over here, I can see that 6 nitrogens are still +5, but if I got 2 nitrogens that went to +2. So that means 2 of the 8 nitrogens gained 3 each. Okay? So gain 3 electrons. That's reduction. So 2 nitrogen atoms gained 3 each. 5 of them did nothing. I'm sorry, 6 of them did nothing. And I get that because there's 2 nitrates, 3 times the whole thing. Lost 2 electrons. I got copper going from 0 to +2. 3 of them are doing that, so I have 6 total electrons got lost. 6 total electrons were gained. Okay, now, who's the oxidizing agent? The oxidizing agent gets reduced. Okay, who got reduced? It's the N. And the way you do this is you answer the whole species. So the answer to this question is, in this reaction, which substance is the oxidizing agent? It is the nitric acid. Okay? Well, I hope you enjoyed this. If you got some problems you want me to do, you could send them to me. I'll write a little video. Bye-bye.